In previous class, we have seen that how to determine critical stresses and strain in rigid pavement due to traffic load or due to temperature variation. In this lecture, we'll see what are the different properties of the concrete and how to determine them, which will be used in the rigid pavement analysis. Apart from that, also we'll see what are the different types of joint and how that joint spacing will be designed in the rigid pavement. Let's see what are the different properties of plain cement concrete. As you already know that plain cement concrete is rigid in nature, its strength is high, it's durable, and when you are mixing them and compacting them, spreading them in the field, they are very workable. So these all are the required property what you look in a plain cement concrete when you are constructing the pavement out of them. You require a rigid, you require a high strength, you require a durability of that concrete, and you require its workability. Apart from the strength or durability or workability, we also required some functional requirement which will be essential for a smooth movement of the traffic. We require safety that is corresponding to a proper friction over the pavement. You require durability that the friction or the roughness of the surface of the pavement should not deteriorate over the time. You require comfortable, smooth and quiet riding quality. As you already know, the riding quality or the noise in the rigid pavement is higher than the ride or the noise originating in the flexible pavement. So here this third comfortable, smooth and ride quality requirement is a critical parameter in case of rigid pavement. The strength of the concrete changes with its curing. Now the curing is the process when the hydration process of the concrete go on and its gain strength. The strength gain with time requires the adequate moisture in the concrete. It requires sufficiently high temperature and time. If you see the curing process of the concrete, let's understand this by this graph. So if I plot the strength after 7 days and 28 days, the curing when you are using only air and curing when you are using water also. So when you are using water, the curing process will be more rapid and you will get a higher strength after 28 days of conditioning or curing process as compared to the strength you will get only due to the curing in air. After the curing process, the concrete will become hardened and its property will be changed from the freshly prepared concrete in terms of its compressive strength, its indirect tensile strength, modulus of rupture and fatigue resistance. These all four parameters, whether it's the compressive strength, indirect tensile strength, modulus of rupture or fatigue resistance, represent the strength of your hardened concrete. So after freshly preparing the concrete, you will cast some samples and you need to test that sample for these test parameters in order to assess the concrete strength. Let's see one by one how these tests will be conducted and what these parameters are. Compressive stress test is performed using 6 by 12 inches diameter cylinder after 28 days of curing. The test sample is shown here in this figure. So after curing process, you will take this cylindrical specimen and you will load the cylindrical specimen to a load. The maximum load taken by this specimen divided by the area will give you the compressive strength of the sample. Typically, the compressive strength of the concrete ranges between 4,000 to 6,000 psi after 28 days of curing. Although the more relevant property to model concrete or to assess the strength of concrete is MOR or modulus of rupture. However, we have good correlation of modulus of rupture with compressive strength. In order to ease the process of calculation of modulus of rupture, instead of directly calculating it, we have an empirical equation to relate this compressive strength to the modulus of rupture. Most of the time, people are using these types of empirical equation to determine modulus of rupture rather than directly testing this modulus of rupture. Indirect tensile strength or the tensile strength of concrete in pavement application is a very important parameter because it simulates the traffic conditions or loading stresses conditions at the bottom of the pavement surface during traffic loading. In this test, the cylindrical samples is loaded diametrically and is determined using this expression, and this tensile strength is also very good correlated with the compressive strength of the sample by this empirical equations. So you can calculate the tensile strength of the rigid pavement or the tensile strength of concrete more precisely by just calculating its compressive strength. Flexure strength of the concrete or modulus of rupture or MOR of the concrete is calculated by using a bending moment test. In bending moment test, this is the third point load bending moment test. Here a beam of 6 by 6 by 20 inches is being used and loaded by two different loads at equidistance point. In this case, the modulus of rupture SC is being determined by using this expression where M is the moment, C is the distance to extreme fiber, and I is the moment of inertia. Here again, this modulus of rupture of the concrete is correlated with the compressive strength of your concrete by this expression. With a repeated number of loads on the concrete, the strength to take the particular fatigue or particular load decreases with increase in number of cycle. To calculate the fatigue resistance, same test as modulus of rupture is being done on the rigid pavement. Here number of repetitions of load is being applied on the samples, and on the each cycle the reduction in the MOR is noted. When the MOR reduce up to 55% of the limit, the number of cycle is noted. Number of cycle corresponding to 55% limit represents the fatigue resistance of your concrete. These are the important properties or important parameters corresponding to cement concrete which will be required in your rigid pavement design. Now, when you lay your concrete in the field, there will be a normal temperature of concrete, let's suppose 25 degrees Celsius. But after this laying work, during the day, the temperature may go up, or during the night, temperature may go down. This variation in the temperature may results in volumetric change in the concrete. Your concrete may expand due to this volumetric change or this change in temperature, or it may contract due to this variation in temperature. Because of this changes in volume in the concrete, you will require some joints in the concrete pavement. So let's see what are the different type of joint required in the concrete pavement. You may have two types of joints in rigid pavement. One is a longitudinal joint and a transverse joint. Longitudinals are the joint along the longitudinal direction of the rigid pavement, and transverse joints are the joint along the transverse direction of the rigid pavement. Longitudinal joint may be uh, required to resist the wrapping or to provide a proper construction stoppage for the rigid pavement. Transverse joint will require to resist the expansion, contraction, and to provide a proper time gap for construction. Let's understand them one by one. Suppose if you have a bigger width of your pavement, the wrapping in the pavement or wrapping stress will be high. Suppose if I introduce a joint here in the pavement, the wrapping stresses which will be continuous throughout pavement width will be concentrated on this part of your pavement. So because of introduction of wrapping joint, the wrapping stresses in the pavement will decrease. You might require to stop the work at the end of day, and in the next day you need to start the fresh work. At this point also you will require to give a joint between old and newer part of your rigid pavement. Suppose you have a big pavement and this pavement start expanding or contracting with changes in temperature. So if the width of the pavement, or sorry, if the length of the pavement is more, there will be more expansion and more contraction in the pavement. So in this case, if you decrease the length of your pavement, the lesser will be the expansion and lesser will be the contraction in the pavement. For this, expansion and contraction joint will be required. The expansion joints are the joints to allow the expansion of the pavement due to any rise in the temperature with respect to the construction temperature. Mostly they are provided in longitudinal direction, or they can be provided in the transverse direction as well. The design of expansion joints involves finding out the spacing of the given expansion joint thickness. Suppose I have a slab of length LE and the maximum expansion what can happen in this slab due to the variation in the temperature is being estimated by this delta dash. So you need to provide a gap between the next slab by an amount of 2 delta dash to accommodate the expansion of the concrete between two slabs of the rigid pavement. So the spacing of the expansion joint or the expansion joint gap should be 2 times of delta dash, and LE should be the length of your slab. This is the typical picture of an expansion joint. So the reinforcement used in the expansion joint should be bonded in one slab and should be non-bonded in the other adjacent slab of the rigid pavement. And this is provided at the middle of your slab thickness. Next is contraction joint. The purpose of the construction joint is to allow the contraction of the slab due to fall in the temperature. The movement is restricted by the subgrade friction. The design involves the determination of the slab length. The slab length is determined by using this expression. That means after this length of slab, next slab will be required, and you need to put a joint or a short joint between these lengths of slab in the rigid pavement. This is the typical picture of a contraction joint. So here in the both end, these bars should be bonded with the pavement, and this reinforcement will also be at the middle of the slab.